This call is now being recorded.
This video lecture will discuss about a convex optimization. So if we go back to an overview of optimization problems, let's go back to this mind map again. We have explained that you can categorize an optimization problem in many ways, looking at the linearity of the problem, looking at whether it has constraints or not, or to look at the type of variable. All right, so one aspect is to look at the convexity of the problem, and this is our this is our lecture in this clip. A convex problem plays an important role in applications because by the property of the problem itself, it has a very nice result, nice theory. I will explain shortly that a benefit of having a convex problem is that you don't have to worry about a local minimum. Okay, a local minimizer that you have found is guaranteed to be a global minimizer. Okay, in order to talk about a convex problem, there are two concepts that that are very essential. The concept of a convex set. This is a convexity of a set itself. It will use to describe the constraint set. And another concept is the convexity of a function. Okay. Very first one. We say a convex set. A convex set is said to be a set is said to be convex if you pick any point, any 2 points in that set, and you make this special combination. This combination says that you pick any scalar between 0 and 1, okay, theta x plus 1 minus theta y. Okay, if this is a point x, this is a point y. Okay, when you make such linear combination where your theta lies between 0 and 1, that point z is going to be some point on the line between x and y. Okay, for example, if z is a midpoint between x and y, that corresponds to this combination using theta equals 1/2, right? If theta is big, closer to 1, if theta is closer to 1, your point z is moving toward x and vice versa. Okay, such combination is seen a lot. This is called linear combination. Alpha could be any real number, but when alpha 1 and alpha 2 are kind of related in this way, this is called a convex combination. Okay, a convex combination. Okay, now I go back to the definition again. We're not done yet because a set X is said to be convex if you pick any 2 points on that set and the convex combination of those 2 points is still in that set. If that's the case, if this condition holds for all choice of x and y, for all choice of theta between 0 and 1, that set is called convex. A typical example would be like, oh, if this is my set, okay, if I pick any 2 points, okay, and I consider all the points on the line connecting those 2 points, any convex combinations, right? You see that this region is still in that set, right? Regardless of my any 2 points, okay? The blue segment is still in that set, and I can do it for any 2 points in the set. All right, I pick any 2 points in the set. The convex combination is still in that set, so that green set is convex. On the other hand, if I have only the green circle, which doesn't include the region inside, this set, whether it's convex or not, I'm going to pick any 2 points, right? I'm going to pick any 2 points on the set and I consider the line segment between those 2 points, and you see that these guys do not belong on that set. So this set is not convex. Okay. The definition is that in order for a set to be convex, is that you pick any 2 points from the set, and you make a convex combination. This special combination, this is a new vector. All right. You check whether these new vectors still belong to the set or not, the set in question. And if this holds for all theta, and like theta between 0 and 1, and it holds for any 2 points that you pick, then the set is convex. You see that from this set, if you pick these 2 points, this guy, all right, this is a vector. Oh, sorry, this is a vector theta x plus on that, right? This part doesn't belong to the set C. Okay, so the circle, this green circle, is not a convex set. What about this one? Naludom, is this set convex or not? If I pick this point, 2 points, so if you see this, it basically, it literally means that there are 2 ellipsoids, all right? You have to interpret the shape as if you see it. This doesn't mean that, the region, okay? Like you see 2 ellipsoids. This is not a convex set, because if I pick any 2 points and I see that a convex combination of these 2 points now do not in the set, all right? It's not in the set, sorry. Now, if I change the set a little bit, if I change the set so that it has a donut shape, is this set still convex or not? It's still not a convex set, because again, if I pick this point and this point, right? And again, there's a part of the line segment that stay outside the set. This is not a convex set. The star, is it convex or not? No, it's not convex. Now, looking at the mint color only, the set C is supposed to be this line. Is this convex set? Why is it convex?
For the star,
Mm-hmm.
all the points within the shaded region will shaded.
Oh yes. If I pick these 2 points, right, these lines stay inside, but it has to be whole for any pairs. Whole for any pairs of x and y. Counter example. How should I pick those? If I pick like 2 vertices, right? These parts stay outside. Now, if you draw something, you say that the set cannot have like the part that's moving like toward inside, because it's gonna violate the condition by picking this example of 2 points. The mint color. If I pick these 2 points, of course, the line segment is still in the set. Okay. If I pick these 2 points, the convex combination is still in that set. Yes. So the mint green, the green mint color is a convex set. What about the purple? If this is number 2, can you describe this green color? How can you describe it in terms of equation? Nacha. X1 No, x1 plus x1 and x2. We don't have y. Equals 2. Okay. Now, can you suppose this is 1. Can you describe the purple equal to 1? But the purple line is just this. It's just the segment. Both x1 and x2 or just x1? Both x1 and x2 must be between 0 and 1. It's okay. I mean, in application, you are the one who introduce constraints. Okay, like this is an example of constraint set. I mean, the reason why we discuss about convexity of set because, like further, we gonna consider our constraint sets whether it is a convex set or not. So what I ask you to describe this set in terms of mathematical equation is just to recognize that, oh, this corresponds to this constraint. Okay, a lot of time when you introduce constraint to your problem, you don't want your constraints to be redundant. Yes or no? If you say, oh, my x2 is less than 2, you don't want to introduce this. Like you pick which one do you pick? I mean, if these are connected with and, right? Of course, which one do you pick? Do you mean this one, right? Only the first one. You want to think about that again? The purple thing? Huh?
Only x1 or x2.
Only.
Of 0 to 1.
And then if you restrict x1 to be only 0 to 1, you get this portion, right? That's one thing. Okay, that's possible. Or you can use x2. Or this is possible. This is all possible. Or x1 and x2 are positive, right? This one you will see, like it will be more common for you to see this type of constraint. Because it's called probability simplex that we just I think we mentioned it previously. Now what about the purple thing? The purple thing, is it convex? Is it convex? Convex? No? Yes. It is convex. This is convex. Okay. Okay. So I think so if I don't go through mathematical expression, if I just draw it freely, okay. The first one, is it convex? Maybe it's not clear. The first one is convex. The second one is not, right? Obviously. Maybe it's too easy. What about just a rectangular box? What if I now I have another set, the yellow thing. Now I have two sets, all right? I have two sets. Now the union of these two sets is convex or not? No, obviously not. If I make an intersection of these two sets, Yes, okay. One thing to notice is that, oh, the set C1 is convex, the set C2 is convex. The intersection of these two sets is also convex, okay? Even though I illustrate with just a particular example, but I just give you a fact, all right? But it's not hard to prove, okay? An intersection of convex set is convex. Maybe homework number 2, because this is really not too hard. That's why when you have a set of linear equations, if this is your constraint, is it convex or not? So you can think of one equation as a line, right? And then because it has to be satisfied with all the equations, so you can think of that as the intersection of many lines. And then the set of solution to a linear system is a convex set. Okay, maybe just for now. Next, I hope that with this definition, the goal is that if I give you some mathematical expression of a set, I hope you can draw it. Okay, like circle, parabola, ellipsoid, box, hyperplane, and then you can verify whether the set is convex or not. Okay, now let's talk about the convexity of a function. A function is said to be convex if this inequality holds. Okay, on the left hand side we say this is you have any 2 point x and y. Okay, these x and y belong in the domain of the function f. You make a convex combination of x and y and then evaluate in f. Okay, on the right hand side you evaluate fx and fy, and then you make convex combination of fx and fy. All right, different operations. If the function of convex combination of x and y is always less than the same convex combination of fx and fy, the function is said to be convex. A typical explanation, you will see this a lot. Okay, you will see this a lot. If I pick any point x and any point y, all right, where is my convex combination of x and y? Where is it? This is the axis of fx. This is the axis of x. This is just say, oh, any point x, any point y. Convex combination of x and y. Where is it in this sketch? Where is the vector theta x plus 1 minus theta y? Is it on the x-axis or on the y-axis? วรชิต On the x-axis, what portion? Right? Right? This is yellow region. This is the point theta x plus 1 minus theta y. Now, where is fx? Where is fx? Here. อุ๊ยตาย This is my this is my fx. This is my fy. Right? Where is my convex combination of fx and fy? Where is it? Between fx and fy. Okay, so this is the right hand side of the inequality. Okay, and then so what's the meaning of this inequality? Hmm? Oh, what is f of the yellow thing? F of the yellow thing. So it has to be what? Yeah. So you're taking a look at you're taking a look at it's this curve, right? And you see the value on the y-axis. So this inequality means that maybe it's not clear because the shape I'm drawing, okay? Because of the shape no, it's not good. Okay. So which means the green part, if you look at the value, has to stay under the line connecting fx and fy. And it must be whole. It must hold for any point x and point y. If I draw again, okay. If I pick any 2 point x and y here, okay. If I draw fx and fy, the line connecting fx and fy, if my function value under this portion lies under because of the inequality, okay, if this hold for any point x and point y, any pair, the function is said to be convex. Now let's take a look at some non-convex function and see why does it violate this condition. Now this is an example of non-convex function. These if I pick x and y to be this pair, you will find some pair of x and y, right? Now if I draw a line, if I, if I draw a line between fx and fy, I see a portion of my, again, this is convex combination of x and y, right? This is the left hand side is above the right hand side of this condition. So you found some pair of x and y that, oh, this condition does not hold. So the function, this is the concept of convex function, but geometrically, loosely speaking, a convex function would have, if it's one dimensional, if it's scalar function, it's something that have an upward shape. Okay, if f is function f, similar, related definition would be f is called concave if minus f is convex. That would be the term that you might have seen in some resources. Function is concave if minus f is convex. So a concave function would look like this. In application, for example, likelihood function, when you do the estimation, is typically have a concave property. When you have a function that is concave, it makes sense to what? To maximize. Now I give you a typical example of convex function. Now we will not have time to verify the property of all of them, but let's just focus on one thing that is very simple. Ax plus b. This is f5 function, right? This is f5 function. If a of, now you verify theta x plus 1 minus theta z, okay, plus b equals what? Equals theta of ax plus what a, no, I should a z minus what? A theta z and plus b, right? And for plus b, how should I make it? I would like to see whether it satisfies this condition or not, all right? So I'm going to try to write theta as, now I put this theta and ax plus b, okay? I use this b, and then I try to write 1 minus theta az. Did I forget some terms?
Theta is not in the B terms.
Oh, yes. So if I have theta b here, right, I would get, I mean, it will compensate with this because here I have minus theta b, and here I have theta b, and then I have 1 times b from the original term. Right. These satisfy with equality. So Fi equation, Fi function satisfy the convexity condition with equality, and Fi function is convex. Exponential function, we're not going to prove by the definition, but I would like you to see the shape of exponential function, that it has an upward shape, okay? The absolute value, okay? The absolute value and with the power. So it's going to look like this, when p is greater than 1. What if when p is 1/2 square root? What is the graph of square root x? Is this, right? Is it convex function? No. Okay. Now extend to a function in Rn. This is a Fi function, norm function. Sketch real quick. Why is norm a convex function? Because if I consider theta x plus 1 minus theta z, okay, what do I get? I'm gonna apply property of norm, triangle inequality, that says this is less than the norm of theta x plus norm of 1 minus theta z. This is property of norm, okay? And then I'm going to use homogeneous property of the norm. Norm of theta x is Pirapong. Like theta is just a scalar. Norm of 2x is, yep, absolute theta. But because theta is between 0 and 1, so it's basically theta, right? And 1 minus norm of z. So this is very important. Any norm, whether it's a vector norm, matrix norm, any norm is a convex function. Okay. Quadratic function is convex. Okay, we're gonna come back to verify it, but I'm just giving you the information here. Norm of Fi is convex. Negative entropy function for, I mean, this is a scalar case. I think this is in your homework, right? Function x log x, if you plot, it looks like this. It's a scalar case. When you extend into the vector case, when x is a vector, it's a function of sum xi log I. Okay, what time is it? Now, this plays a very important role in binary classification. I hope you see something in something like cross entropy that looks like this term when you train the neural network as a classifier. You see the cost function that looks like this. Okay. Now there's some important fact. I will not prove then. Connection. There's a connection between convex set and convex function. Okay. If you describe a set by inequality like this, okay. If the function fi are all convex, this is I from 1 to m, okay? This set is a convex set. Which means, it basically means what? First, we know that an Fi function is is convex, right? So if you have a set C that say, oh, you have A transpose X less than B, okay? You have X transpose PX plus Q transpose X less than 2 when P is positive. Then you can claim that, oh, my F1 is what? Is A1 if it's A transpose X minus B. This function is convex. Okay, my F2 is quadratic. It's quadratic function, right? And because my P is positive definite matrix, positive semi-definite matrix, you use this fact that, oh, my F2 is also convex. Okay, if I make an intersection between these two constraints, right? When you say comma, it means that each constraints are related by and. You make intersection. You say that, oh, this set must be convex. I mean, the proof is easy, but let's just skip it. Okay. It's okay if you want to try to prove it because but it's very important. Let me state some real quick fact. Now you see that a lot of times you can check convexity of a function by using the definition, but I'm going to give you another two conditions related to the derivative that will be used to concluding the convexity of a function as well. When a function f is convex, all right, oh sorry, suppose f has a gradient, which means it's differentiable. Now I'm stating a first order condition that equivalent to convex definition. The function f is convex even only if fy is greater than, now I want you to take a look at the right hand side. What is this thing? Your homework. What is it? The first order approximation of which function? Function f, right? Of f function at which point? At point x, all right? So, or in other words, this is a tangent plane of your f, okay, at point x. So if these conditions hold for all x and y, all right, first order condition hold, we say that guarantee your f is convex. Graphically, this is your fx. Suppose this is the point x, okay? The right hand side is my what? My tangent line. The slope here has to be the same as the gradient of my graph, right? So this for first order inequality says, so this is this line described by the right hand side of the inequality. Okay, so it basically means that my f is going to be convex if I have a tangent line at any point. Okay, it can be any point, and my graph always lie above the tangent line. No? Like, oh, sorry. If I verify on this point, it still holds. Okay. Now let's see how this equation, how this condition is not satisfied for non-convex function. Because if I draw, where should I draw? Like, for example, I draw here, right? This is my tangent line, my first order approximation of my function at this point, and my graph line below. So this function is not convex. Okay. There's a meaning of this, and this is related to your last homework. I asked you to plot a surface of quadratic, and I asked you to plot the tangent plane, and I asked whether you observe that the tangent planes always lie underneath the surface or not. Actually, I just want you to do experiment, no need to explain. But the explanation is this. Because your quadratic function is convex when P is positive semi-definite. So that's why the first order approximation always lies underneath your function. Okay, so that's the reason. The second order condition is also important because actually it provides a practical way to check convexities as well. A function, if the second order exists, if you can find the Hessian, you can check the convexity by checking that if the Hessian matrix is positive semi-definite or not. This is related to your previous knowledge about verifying local min, local max, right? For a scalar function. Now, okay. The reason why you need to check the second derivative is to check the rate of change of the slope. Okay. Does it make sense? A convex function. If you draw this is just a slope, right? But can you see that the slope is always increasing? On this side, the slope is negative. It's less negative. The slope is 0. The slope start to be positive and start increasing. Make sense? This is a scalar function, but for a function of several variable, you describe it as a Hessian matrix. Go back. So from that, this is an explanation of why a quadratic function is convex, because if we use the second order condition, the Hessian is P. Okay, so that's why the condition is here. A quadratic function is convex even only if the matrix P here is positive semi-definite. Okay. Now let me give the definition of a convex problem. Okay. Now you have learned the concept of convex set, convex function. What about convex optimization? A convex optimization is a problem of the form of minimizing f naught that is convex with the linear inequality constraints where fi is convex. With the equality constraint, only the case of f5 function. Okay. Now, what's the difference? So you have the universe of all optimization problem, okay? And now a convex op is just a one subset, a big subset, because now you only talk about objective that is convex. Does it make sense? Like any function in the world, right? The universe and convex function is a subset of them, right? So that's why convex optimization is just a special case of a standard optimization problem. Now pay attention to the constraint. The constraints. Now we previously just learned that an fi function is a convex function, right? And we also learned that the set C that described by what? By inequality that associated with convex constraint, convex function, this set C is convex, right? The set C that described by F5 linear equation, it must be convex as well. Okay, it must be convex as well. The intersection of two of them, as we learned, intersection of convex set is a convex set. So in short, a convex optimization problem is a problem of minimizing convex objective, and the constraint set is convex. Now maybe what about what if I have the set C that described by this? Now pay attention. Is my constraint set convex or not? Because of, you can say, oh, because of the equality constraint, because of a linear inequality constraint, because of which one? Which constraint? Because of equality constraint, right? This equality constraint is not affine. And we all know that from the previous example, this what is a circle, and a circle is not a convex set. Okay? LP. Is LP a convex function, convex optimization? Yes or no? Yes, because the objective is linear, right? This is what? Yeah. So gx less than h is just a bunch of f5 function, right? So you say, oh, my fi is what? Gi transpose x minus h. This f5 function is what? Is f5, and then we know it's convex. So LP is convex. What about QP? Is my QP, standard QP, a convex optimization or not? Obviously, the constraint set is convex, but what about the objective? Only P is positive semi-definite. Okay. We have the result. We're not going to prove, but it's very, very important. An optimal solution of a convex program is guaranteed to be a global minimizer. Okay, not just a local minimizer.
So, explain this one.
QP?
Yes.
Because the definition of a convex program is that you have to minimize a convex objective subject to convex constraint set. Because QP has a constraint set as a polyhedron, which is obviously a convex set, but the objective, which is quadratic form, whether it's a convex function or not, depends on P. We have seen previously that a function is convex even only if the Hessian is positive semi-definite and the Hessian is matrix P. Okay, now we're almost done. I mean, this is a very important result. Usually we like explain the proof and everything, but now it's just enough for you to like recognize this fact. Of course, if we explain by just a scalar one-dimensional function, because the convex function is like something upward shape like this, I mean, it's obviously see that, oh, you have only one local minimum, and that one will be a global minimum, unlike non-convex function. Okay. Now this is a lot, I know, but I'm going to highlight only some of them that is very important. When you have, because of this property that a convex problem has a global solution, there are many efficient algorithms to solve a convex program. Then it just only takes a lot of work to see if a problem is convex, because of in terms of algorithm, if you solve a moderate problem, then we have many efficient tools. Okay, that's why the property of convex problem is important to recognize. Here it says that, here I want to highlight some of them. When we talk about a convex set, if you have an intersection of many convex sets, the intersection is also convex. Okay. we'll talk about operation that preserve convexity of a set or convexity of a convex function. Okay, for now it's okay to learn about the intersection of a convex set is a convex set. Okay, now for the preservation of convexity of a function, first one, if you have f1, if you have two functions f1 and f2, both are convex. If you do a weighted combination of two functions, and if those weights are non-negative weights, all right, the non-negative weight sum is also a convex function. The claim is easy to see because we can check from the second order derivative. What is the second derivative of g? Thanapat. G, the new function, is weight f1 plus weight f2, right? Let's say f1, f2 have Hessians. What is the Hessian of G? Theta 1. This is fx. This is the sum of functions. You have two functions, make a sum. Find the second derivative. Theta is just a weight. It's just a scalar. Pirapong. The Hessian of f1, right? Plus theta 2 Hessian of f2. Okay. Now, if I use the second order condition, our function is convex if the Hessian is positive semi-definite, then is it clear from here? Because by assumption, if f1 is if is convex, this guy is positive semi-definite, this guy is positive semi-definite. If theta 1 and theta 2 are non-negative weight, simple result, you have two positive semi-definite matrices. If you sum them up, the new matrix is positive semi-definite. So your G is still convex. No? Yes? Which means, if my objective is this, my objective is convex or not? Yes, because, the linear function is convex. Okay, maybe. The norm square is just the quadratic function. You can claim that, but maybe I change a little bit. Norm one. Any norm function is convex, all right? Okay, so the total is convex only if my gamma is non-negative, okay? What else? Maybe just that, okay? Like use this thing to conclude. Maybe I give the last property because these appears a lot in application. If you have composite function with f phi, composite of convex function with f phi, your f, suppose my f is convex, okay? My gx is composite of f with f phi. Got it? This is given. My f is convex. This is a composite of f with f phi. The result is that the composite function like this g is also convex. Example, norm square is convex. If I composite it with f phi, convex or not. The result is convex. Again, Chebyshev approximation. Norm, infinity norm is also convex because it's just a norm. I do composite with f phi. So this whole function is convex. Again, what happened? My e to the a transpose x plus b is convex because I know that e to the x is convex, right? And I composite with f phi. So the result is convex. What about -2? Huh? -2. E to the -2x, is it convex? Huh? Is it convex? Yes, right? So the whole thing is also convex. Okay, let's just say that actually there are many more properties that preserve the convexity. Usually I teach this in convex optimization, but for now, let's just say that it's only enough to understand this property. Where is the lecture? Okay. Last message. A convex problem is a problem of minimizing convex objective with convex constraint. Okay. Clear. LP and QP are example of convex program. Okay, let's stop here.